Please, hello everybody. You are welcome to our Kharkiv Quantum Seminar. And today it's my great pleasure to introduce today's speaker, Peter Hommelhoff, who will speak about ultra-fast coherent electron dynamics in light-dressed graphene. With the next one slide, I would like to briefly introduce Professor Hommelhoff by telling briefly about the biography. He is a professor of physics at Ludwig Maximilian University in Munich since last year. Still, he continues to be with the Friedrich Alexander University in Erlangen, where he was appointed full professor position in 2012. He received the diploma in physics from the Swiss Federal Institute of Technology, ETH, in Zurich, at the border of millenniums. And 3 years later, the PhD thesis he defended in Munich. From 2004 through 2007, he was a postdoctoral researcher at Stanford University. Then he headed an independent group in Max Planck Research. In 2012, he received the habilitation in physics, which I think is analogous and close to our Doctor of Science degree. This was in, again, Munich. And then he became the director of the chair of laser physics at the Erlangen University. In 2018, he was elected a member of the parliament of the German Physical Society, DPG, which is known as the largest physical society worldwide, even larger than the APS, which is going to have much meeting next week. Once I was at the DPG spring meeting, very impressive. So many brilliant talks, so many sessions in parallel in Dresden and in Berlin 2 times. Dr. Hommelhoff is a recipient of the 2020 Leibinger Innovation Award and of the 2022 Gottfried Wilhelm Leibniz Prize, which is Germany's highest research award. And having said you about this brief introductory information, I would like to give the floor to our today's guest, Dr. Peter Hommelhoff. Please.
Thank you very much. Give me 1 second to just share my screen. Here we go. Great. Can you see my screen? Perfect.
Yes, full screen.
Thank you. Thank you very much. Thank you very much for inviting me. It's a real pleasure that I can speak here. And I should say I'm joining you from Erlangen, which is 20 kilometers away from the city of Nuremberg, that happens to be one of the partner cities of Kharkiv. And I'm particularly happy that Nuremberg is one of the partner cities of Kharkiv. This talk today will be about ultrafast coherent electron dynamics in graphene and also in light-dressed graphene, what you can see down here, where we can now just take one light field and really change the properties of the material that we're interested in. But let me first show you why it's interesting. Of course, from the fundamental point of view, we all love it to do new physics, explore new physics, but it might also take us somewhere. And let me show you where I think this could take us. And the buzzword here is petahertz electronics. You all know that for electronics, we really have to control electrons on the time scale of roughly nanoseconds, or maybe 100 picoseconds. This is the basis of today's electronics. And we'd like to just look at the same, but change the units. We'd like to do that basically on femtoseconds and just control electrons by virtue of the light's carrier field. In this way, approach basically a bandwidth of the inverse of 1 femtosecond, so roughly petahertz, or do what people call also light wave electronics, to really steer electrons right with a light field. And I'd like to show you where we stand, how we do that, and what kind of interesting physics is behind it. So to control light waves and to really measure light wave effects, we can't use CW fields. Why will become clear later, but we have to resort to very short laser pulses. And these laser pulses are just roughly 2 optical cycles short. So this is a little bit of an exaggeration here. This is just a maybe single cycle or even sub-cycle laser pulse. But what's important is really now the optical field shown as a red line here, and not so much the energy content. So we'll be really dealing with a field structure. And for now, more than 25 years, this can be controlled. So we can control the exact field underneath the envelope of such a laser pulse by what's being called the carrier envelope phase. The carrier envelope phase is just the phase difference between this carrier maximum that you see here and this envelope maximum shown in light gray. So this, for example, here is a pulse with a carrier envelope phase equal to 0. And here we've just shifted. You see there's now a phase difference of roughly pi/2. And we'll be using a lot these carrier envelope phase controlled laser pulses to really steer and control electron dynamics. So this will come back several times. Now we're interested in really exploring strong field physics in solids. Why will also become clear in a second. Why is it interesting? We all know when we're in the weak field limit, we can basically only drive transitions that are resonant with the frequency of the light. Then this photon picture holds, and whenever we hit a resonance, we can drive electrons, for example, from the valence to the conduction band. So the photon energy basically has to match the bandgap. This is very different when we go to strong fields. When we go to strong fields, what happens is we can drive electrons within a band, either within the valence band, or we can drive them within the conduction band. And then it happens so that the electrons can just undergo a transition here, even though the light is not resonant with the bandgap. I will show you in a second in more detail. But this is what's so exciting about strong field physics, that intraband motion and interband transitions are now intricately coupled. And this is basically the essence of strong field physics. We have to consider a joint picture of intraband motion and interband transitions. A lot of beautiful stuff has happened ever since basically the first observation of strong field physics inside of a solid. This now dates back 14 years, so it's really also a maturing field. I'm just showing you here a lot of papers, a lot of observables, where people mostly looked into high harmonic generation, that I'm sure you've all heard about, especially after last year's Nobel Prize. We're focusing more on ultrafast charge transfer. So we're more interested in, can we look into currents that are driven between 2 electrodes? And I'm going to focus on this system here, where we look at currents induced by the laser field inside of graphene. So this is really, for the remainder of the talk, this is the system that we're going to be looking into. And I really like to show you what's going on there in terms of interesting physics. So just to set the stage, you all know graphene, this beautiful single layer of carbon atoms that are hexagonally arranged in real space. And then when you go to reciprocal space, we got this very interesting band structure where at these K points, the valence band at the conduction band touch. So we have this very famous Dirac-Cohn dispersion relation, but the valence band down here touches the conduction band at this Dirac point. And we will drive electron dynamics in this band structure. But it's actually, the band structure, as you will see, is not so important for us. We just need a band structure to base our physics on. And this happens to be graphene. And then what can happen? So let's go back and just see what can happen to an electron that is now exposed to a strong laser field. Let's just look at one slice in this band structure. The laser field is now only polarized in X direction. and we just shoot a laser field. And then what happens is intraband motion. Intraband motion is described by the famous Bloch acceleration theorem, where we can just follow any initial crystal momentum of an electron. And we know how it depends on time by this expression. So we just need to look at an initial crystal momentum and then take the vector potential of the light field to understand what's the dynamics of this momentum of the electron. And the vector potential, just as a reminder, the vector potential of a light field is just a negative time integral over the electric field. That's the vector potential. This is responsible for intraband motion. This just drives the electrons. And then what can happen here, if we inject an electron here, you see there's a relatively small energy difference. Here the electrons can just do a Landau-Zener transition. So here the electron can just tunnel up, if you will, from the valence to the conduction band. And this transition is described in this impulsive limit by this famous Landau-Zener formula, where delta is the band gap and alpha basically encodes the speed with which the electron is injected here into this avoided crossing. So we need these two ingredients, but that's basically it. We don't need much more to understand what's going on there. And we'll see it. I show you that it's really beautiful physics that results from the interplay of this intraband motion and these interband transitions. So let's look into this a bit more in detail. When is the strong field regime reached? You've probably all heard about a very famous parameter. It's the Keldysh parameter, named after Leonid Keldysh, who unfortunately passed away something like 5 years, I believe. And the Keldysh parameter is a dimensionless number that encodes the carrier frequency of the laser, the mass of the electron, the band gap, and the amplitude of the laser. And every time the Keldysh parameter is larger than 1, we're in the weak field regime. When the Keldysh parameter is smaller than 1, we're in the strong field regime. When are we in the strong field regime? When the amplitude of our laser is large, when the frequency of the laser is not too high, and when the band gap is not too high. Then we're in the strong field regime. But what's interesting, we can also rewrite the Keldysh parameter a bit. And then at resonance, we see that the Keldysh parameter tells us what's the ratio of laser angular frequency and Rabi frequency. So when the Rabi frequency, so the rate of change of an electron going, for example, from the valence to the conduction band, when this Rabi frequency is larger than the laser angular frequency, then we're in the strong field regime. And this is, of course, something super interesting, right? When you realize that we drive a system so hard that it's more likely for an electron to undergo a transition within an optical cycle than not, then this is of course super interesting and a very interesting regime to look into. Just to show you, this is just from model simulations, what this means. Here's just a few cycle laser pulse, and down here I'm just showing you the probability for an electron to be excited to the conduction band. Initially the electron is in the valence band, and then comes the laser pulse, and here you see that basically over the course of the entire laser pulse duration, the parameters are such that at the end the electron is in the conduction band with unit probability. But it's really, it basically takes the entire laser pulse duration. You see here some kinks and steps, somehow reflecting the sub-cycle structure here, but it's basically not really resolving what happens during a single cycle of the field, even though this is already a pretty strong field. Very different here in this strong field regime. Here you see now that even over here, when the field amplitude is not so large, we get a very high probability for an electron to quickly go into the conduction band, quickly go back, stay in the valence band, go back up into the conduction band, go back. And this is not a random process. And I'd like to show you what's going on here. But here you see just the strong field regime in action. The electron dynamics is much faster than one optical period, right? I mean, you see here from basically 10% of the electrons being in the conduction band up to 90% is much less than half an optical cycle. So the dynamics is really field resolved, and the excitation really happens easily within a cycle of the laser field. This is the strong field regime, and we're trying to understand this. Let me just show you one already here, this intro part, one figure that somehow summarizes a little bit what's going on here. And this is a complicated figure, but I think it's worth it looking into it. Down here, we now plot the Keldysh parameter. Keldysh parameter 10 means it's a weak field regime. Keldysh parameter 0.1 means we're really deeply in the strong field regime. And now what's on this axis? On this axis is the bandwidth of the material measured in units of the photon energy. So, excuse me, m equals 1 means that we're on resonance. So we can totally understand what's going on here. Here we just see that, all right, at resonance, we just get electrons into the conduction band. This is what's plotted here. Oh, sorry, I should say that. What's plotted here in color scale is what's the fraction of the electrons in the conduction band after the laser pulse is over. So we're now just looking into the residual conduction band population when the laser pulse is over. And you see here, of course, the largest action happens on resonance as expected. Then we just see that even on resonance, we don't get any excitation. This is just Rabi flopping. So we just see Rabi physics that also, even though there is light, we don't end up with electrons in the conduction band. So this would just mean that we drive the electrons up and drive them coherently down again. This way, there's no electrons in the conduction band here. And then this goes really towards carrier wave Rabi flopping. And now what's very interesting to realize is that down here, there's no conduction band population. Why is that? Well, that's very simple. Down here, there's hardly any band gap. So the laser pulse just drives electrons over the band gap from the valence into the conduction band and back and over the band gap and back. And when the laser pulse is gone, the electrons basically end up where they started. That's why here, there's hardly any conduction band population. Similarly, over here, there's no conduction band population just because now the band gap is large and the field is small. So here we just don't get any excitation. And this zoo here, this is the interesting one. What's going on there? We can now have a band gap off resonant. We can have off resonant driving and still get crazy dynamics here. And let me just take it as a spoiler. I'd like to show you what's going on here in this talk, and I'd like to show that super interesting physics that is actually closely related to the work of our seminar organizer here, as you will see.
Excuse me.
Please.
May I ask a question? So in the regime of small band gap, you said that you drive the system and it falls back. But
Yes.
Actually, I think there must be some energy transfer from the field to the system. Why they fall back?
It's basically as if there is no band gap. It's just coherently driven. And the energy is actually not really transferred. So when the electron ends down here where it started, you drive it, but you have not pumped energy into the graphene. Hence, no energy transfer, basically.
Oh,
Does it make sense?
Yeah, thank you.
Thank you. Thanks for the question. Okay, we can skip this here. Let me show you what we do. And we'll get back to the physics in a minute, of course. We just take graphene, sitting on a transparent substrate here, silicon carbide, and the graphene is just connected to gold electrodes. And then we shoot these laser pulses and just measure a current. So there's no voltage applied, there's no asymmetry here, it's totally symmetric between these electrodes, and it's in fact the laser pulses that break the symmetry. Here you see a picture of the experiment. The graphene sits inside of a small vacuum chamber. Here you see some wires. We not only have one sample, but in fact we have several samples connected at once. This is just a mirror. So the laser beam comes in from here. The mirror, it's a focusing mirror, focuses the light down on our graphene sample. And over here we have a microscope objective so we can see where we hit the graphene. This is what this microscope objective. This is an SEM image, but you see it's basically what this microscope objective would see if there is an optical resolution for high enough. The black part here is the graphene, so we can have a very short graphene ribbon, longer graphene ribbon, and even longer one. And the size of my little mouse here is basically the size of our laser beam. It fits pretty well. And you will see, so when we put the laser beam here, you see that we not only illuminate graphene, but we also illuminate the gold. And this is going to be important later. So what do we do? Now, I'd really like to show you what's going on both inside of graphene. I'd really like to show you that we can generate a current just because the light field breaks the left-right symmetry. The substrate, the graphene, the gold electrodes are all left-right symmetric, and we only got a current because the laser field breaks the symmetry. I'm going to show you. And I'd like to show you that this leads to a ballistic current purely generated in graphene. And on top, I want to show you what happens if we shoot the laser at this graphene gold interface, where obviously the left-right symmetry is maximally broken. On the left-hand side, we have graphene. On the right, we have gold. Here, still, we generate a polarization. So charge carriers generated here at the interface, which also lead to a field-dependent current, as we will see. Let's look into this again in a bit more detail now. So over here, we now just following this electron. And when I press start, you will just see that we basically run through this field here, or vector potential. Let me show you what happens. So now the electron is just, you see here the vector, we're now here. The initial electron that we follow is just a bit displaced to the left. Now comes the interesting part. Electron is driven to the right. With certain speed, it's being injected here into this avoided crossing. So here can undergo a Landau-Zener transition with a certain probability. Now we continue. Electron goes here, goes back. Again, the electron can go up, or the electron that was driven up here can go down, again with a certain probability, Landau-Zener transitions. And then the laser pulse ends. And here I've drawn it as if the electron is excited with 100% probability. But what now determines if the electron ends up in the conduction band or in the valence band? And this is really interesting to realize. Excuse me, hold on. Before we go there, I have to show you this here. You probably know the very famous Landau and Zener paper, both from 1932. You probably don't know these two papers here, Stückelberg and Majorana, also from 1932. So there was a lot going on almost 100 years ago. These actually even cite these. So we think only today we're in a fast living world, but already almost 100 years ago in physics and physics publishing, the world was actually spinning pretty fast. And I have to point this out to you. I'm sorry that I have et al. Here. Of course, I should have shown all authors, because then you would see that our seminar organizer shows up here as a beautiful review article summarizing not only this initial work, but really also showing with this beautiful type of physics, and I'm mentioning in a minute how it's called, how this beautiful type of physics shows up in all kinds of physics, also including graphene here. What is this type of physics? We can interpret this here, what we just saw, the motion of the electron in the bands down here and up here, and the coupling here. We can basically interpret this as an optical interferometer. We have a beam splitter here. This Mach-Zehnder action here is the Landau-Zener action is basically the beam splitter. And then we have a beam split state where the photon coming from this laser can be in this arm, can be in this arm. And you all know what determines if the photon goes back to the laser or goes here in this fourth arm to the photodiode. It's, of course, the relative phase difference that the photon accumulates in these two arms that determine where the electron ends up. And it's beautiful because it's exactly the same physics here. It's basically two coherently coupled subsequent Landau-Zener events that are responsible for whether the electrons end up here in the conduction band or in the valence band. Of course, I'm going to show you much more in detail what's going on in a minute, but it's important to realize that these events where the electron can undergo an impulsive Landau-Zener transition up into the conduction band or down into the valence band, and these two instances here and here basically represent nothing but beam splitters, meaning that here the electron is in a beam split state, and hence we have now the analogy of optical Michelson interferometer. And now you wonder, okay, what if we want a current? Which waveform? How does the waveform need to look like to get a current? And let's just look at two example waveforms. One waveform is shown here. This is a waveform with a carrier envelope phase of pi/2. You probably remember from my very first slide. Also remember, please, the vector potential is the negative time integral of the E field. So if this is a pulse that looks like a sine pulse, the vector potential, because it's an integral, looks like a cosine pulse. So where the maximum coincides with the envelope maximum. And then we can just look at two electrons. Why do we have to look at two electrons? In order to generate a current, we have to break the left-right asymmetry, right? If we get the same for the electron on the left and the same for the electron on the right, there's no chance to get a current. You have to break left-right asymmetry in the conduction band population to get a current. So now let's just follow these two electrons, this electron 1 here and this electron 2 here, equally separated from the K point. You see what happens to this electron 1. It's driven first to the left, then to the right. Here where there's a star, it can undergo this Landau-Zener transition up into the conduction band. Here it's in the beam split state, goes back, boom, one more Landau-Zener transition, and then the laser pulse is gone. We just leave it sit like this. Let's look at electron 2. Electron 2 is now driven first to the left as well, can undergo a Landau-Zener transition here, 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 here. So it has 4 points in time where it can undergo a Landau-Zener transition. That looks qualitatively very different. So here we can expect to get a current because these two traces are already qualitatively different as opposed to here. Let's look at this here, a pulse with a carrier envelope phase of 0. Just check it out. These two electrons, 1 and 2, basically do the same. 1, 2 Landau-Zener events for the green electron trajectory here, 1, 2 for the blue one. But it's basically the same, only separated in time by roughly half a period. But we cannot measure 1 femtosecond or so at these timescales, so we cannot distinguish when this happens. So here, qualitatively, these two trajectories are very similar. Hence, we'll probably expect that these two guys would end up with the same conduction band population. So clearly, we favor this picture here. And this makes total sense because, as I said, the time integral of the E field is the vector potential. And it's the vector potential that's responsible for driving electrons in reciprocal space. Hence, it's somehow reasonable, or it really makes sense to realize that the vector potential should be left-right asymmetric, which it is, like you can see here. It's the vector potential that's important for driving electrons in K-space. Hence, the vector potential asymmetry should be broken, like I'm showing it to you here. So it makes total sense also from these trajectories. Okay, so let's get a bit more into detail. Let's just model this and really watch what happens if we just model it by just integrating the Schrödinger equation. Nothing special. We take the graphene tight binding Hamilton operator and just look at the current density. So we just need to calculate the conduction band population and multiply it by the Fermi velocity, so just by the slope of the bands, and this gives us the current density, and of course we integrate over the entire Brillouin zone, and then the shifted charge. So what we obtain after the laser pulse is over is just time integral over this current density. And let me just show you a video. I hope you can see it. Before I press start, let me explain you what you're going to see. This red dot here is going to be moving, so you see where we are in time. The laser pulse will just interact with graphene, and down here you'd see what happens around 1 K point. K point is the point where valence and conduction band touch in graphene, and what will show up color-coded is the conduction band population. Let me press start, and I hope it works. If not, please interrupt me and we go back. Now you should see the point move here. Now something is also happening here. You see sloshing of electron contribution left and right, and more electron population building up over time. And now the laser pulse is gone. And this is what we end up with. What is this? So you see conduction band population here around this dashed line. This is single photon resonant physics. So this is just a single photon resonance. The fact that we see islands here and nothing here is again Rabi physics. We also see the second dashed line. This is second 2-photon absorption. So here we have a resonance with a 2-photon process. But what's very interesting is what breaks the left-right symmetry. This is mostly this part here. So it's this part that's responsible for a current. So really something non-resonant between this single photon and 2-photon resonance line. Everything else you see, mostly, there's also something here, but mostly the single photon physics is not responsible for a current just because it's left-right symmetric. Same here, 2-photon physics, mostly left-right symmetric. It's really this non-resonant stuff here and also here that's responsible for a current. And what's very interesting, if we now just leave this sit, right? I mean, this is just Schrödinger equation, so we don't take any decoherence into account. Even when the laser pulse is gone, like you can see here, the charge just accumulates. There's just more current flowing, right? Why? Because the electrons sit here and just contribute to a current. Of course, in reality, then this would just deplete and decoherence would kick in, etc. Everything would relax back. But it's interesting that in this fully coherent simulation, charge or current continues to flow even after the laser pulse is gone. So, and this is, sorry, I should say that this is what people call real charge carrier generation. We excite electrons with a laser to the conduction band, and even when the laser pulse is gone, there's a current flowing, and this is what people call real charge carrier generation. And now, does it help? I mean, what does it, do we observe this? What's going on? Let me just show you pretty old data. Initial data date back to 2017. More recent data are now probably 4 years old or so.
Чую, тепер аж чую.
Excuse me.
It seems to be not the question.
It appeared not to be a question. Okay, thank you. Sorry, I didn't get it. It was probably Ukrainian. Sorry, I don't speak it.
Yeah, it was in Ukrainian.
Thank you.
І що?
Що, мам? Що сталося?
Oh, I see. Somebody is connecting and didn't realize that the microphone is on, right? Perfect. Thank you. I just continue, right? Thank you. Let me show you what we measure. So this is now the blue dots are experimental data. And we just measure a current that's flowing based on these CEP stable laser pulses as a function of the optical field strength. So here we're just increasing the field strength. We change nothing else. We just increase the field strength. And you see here that the current is initially flowing. First positive current, so above zero, say first maybe flowing to the right, and then flowing to the left, and then the current turn over again. So we see very interesting behavior. We see that the current actually is not monotonous, right? Not at all. It even changes direction, even though we only play with the amplitude of a laser field. So very non-monotonic behavior. And first, we just take it as a smoking gun experiment, or for smoking gun evidence for strong field physics. And I'm going to show you that this picture really applies. So we're now a big step further. I want to show you very new data that we really have this Landau-Sehner-Stückelberg-Majorana interferometer picture that's responsible for this very strange behavior that the current first, if you zoom in here, you would see that the current would first flow to the left, then to the right, then to the left again, and here you see how it's even turning around again. What's going on? Let's look into this in even more detail now. For whichever reason, now we start with electrons on the right-hand side. It doesn't matter. I don't know why. We have to ask the students who made that picture, but now we're starting on the right. What do we have? Here's again shown what can happen, how we can get an electron from an initial state in the valence band up into the conduction band within one optical cycle. The electron could first be injected here, make a Landau-Sehner transition, go up here. Now the laser fields flip sign, the electron is driven back, now stays in the conduction band, it ends up here. We could also have this pathway where the electron first stays in the valence band, and only when the laser field flips sign on the way back, it undergoes a Landau-Sehner transition and ends up here. So you see we have same initial state, same final state, but two different pathways. That means, interesting, these two pathways can interfere. If everything is coherent, of course, we can just have this picture But destructive, you could just say destructive interference means the electron goes back to its initial state. Constructive interference means the electron goes back up into the conduction band. And so now what determines if we have constructive interference? Well, it's the phase, like we said initially, it's the phase difference that the electron accumulates over here in this beam split state. But what is the phase difference? The phase difference is, of course, the instantaneous energy difference, right? So just the spacing between valence and conduction band that the electron is in as function of time divided by h bar. So we can just calculate the dynamical phase when we now integrate over the electron being in this beam split state here, integrate over it, divide by h bar, and we have what people call the dynamical phase. This is the dynamical phase that the electron accumulates in this beam split state. And now this is cool, because now all of a sudden we're sensitive, sorry, I should go back. All of a sudden we're sensitive very much to the difference in energies between valence and conduction band, right? EZV is just the energy difference between valence and conduction band. And this is an interferometer. So that's usually the best measurement tool you can have. You can now measure interferometrically the energy difference between two bands. And this is what we set out to do. So here you just see again valence and conduction band of graphene. And when we zoom in here on this slope of the valence band, I'm just showing you three different slopes. These are just three different slopes resulting from a different hopping parameter in the tight binding model. So when you change the hopping parameter in the tight binding model, you basically change the slope of the band, right? You see it here. When you increase the amplitude of the hopping parameter, the band is just getting steeper. So what we did is we now just take the data that you have, I'm going to show you in a minute, and fit it with the hopping parameter as free parameter. And you see here the Fermi velocity, so the slope of the band, is directly proportional to the hopping parameter, which is not so well known, times the lattice spacing. But this you can measure with high precision. You can just from X-ray scattering, we know the lattice spacing very well, but the hopping parameter is not so well known, meaning the slope of the band. And this we can just measure now by measuring the dynamical phase. So this is what we get. It's the same data as before. And you just see here three curves with three different hopping parameters, same numbers as on the slide before. And the best fit value you can read off here, the best fit value is a hopping parameter of 2.9. And then we just also need as a free parameter, basically, some kind of an effective area, not so important. So this is physically not too meaningful. This is what's really interesting. And from the hopping parameter, we can directly calculate the slope of the band, so the Fermi velocity. This is what we get, 1.07 plus minus 0.04 nanometer per femtosecond. And we had no idea. Is this good? Is it not good? No idea. And then really after the measurement, I can tell you, I dug out three different other numbers. I believe I did it already, no, 2 years ago again, or 1.5. From infrared spectroscopy, scanning tunneling microscopy, ARPIS measurements, they have all access to the Fermi velocity. And we were really thrilled to see that our value within the error bar really matches perfectly what other people have measured. So this Landau-Sehner-Stückelberg-Majorana interferometry is not only something how we can think about the physics, but this interferometer is really a useful interferometer. We can really use it to measure band structure properties of graphene. So we were really thrilled to see this. It seems to be really the basis of the physics, and everything matches to the quantitative level on the well, roughly whatnot, I don't know, a couple % level, as you can see here. So we were very happy to see this. We don't exactly know what's going on here. We'd love to figure out more. We're now getting deeper into this, and we really want to understand what's going on and fully understand if we also see more oscillations here. For this, we're just setting up a new experiment. So much on the graphene, or on the electrons driven inside of graphene. Let me just also show you that it's also interesting to look at these maximally symmetry broken graphene gold or gold graphene interfaces. So what happens when we drive electrons there? Now, it's clear already. Now we're in a real space perspective, right? This is real space. This is just graphene and gold. So now the coordinate is x and not kx. Here it's clear in real space, it's the electric field that drives the electrons. So it should really also be the electric field symmetry that should be maximally left-right broken. And we can see this, or we can understand this. I'm not so sure if you saw it in this little animation. This electron here on the right is driven slightly deeper into the gold than this electron on the left here. And let's put it this way, it's still up for discussion what exactly happens. But just because the electron on the right here is driven deeper into the gold, we just say it's somehow more likely for the electron to be trapped here. It's really just put a chain, trap the electrons, and because the electron is driven deeper on the right-hand side than on the left-hand side, we see more electrons accumulating on the right, which of course then would also show up as a polarization and a current. Our theory friends at the University of Rochester around Professor Ignacio Franco measured this in a real space simulation. This is really requiring supercomputer to measure this. And here you see what's interesting. The gray is again the electric field. The red is the instantaneous charge accumulated in the gold electrode here. And what's interesting, when the laser pulse is gone, the charge stays constant. If you think back 10 minutes, the charge still accumulated after the laser pulse was gone, meaning that this was real charge carriers. This, when you have charge accumulation only during the action of the laser pulse, but not afterwards anymore, this is what people call virtual charge carrier generations. So we see apparently a different physical process, virtual charge carrier generation at the current that results from polarization. Do we see this? Here now come our different samples into play. We can now shoot our laser beam on this 5 micron long graphene ribbon, on a 2 micron long, on a 1 micron long, and here you see the electron pulse overlaps also a lot with the gold electrodes. And watch what happens. Here I'm showing you the carrier envelope phase-dependent current as function of field strength in these plots that we call Firefox plots for obvious reasons. You see here, this is 1 volt per nanometer field strength, 2 volt per nanometer, 2.5 volt per nanometer field strength. And the angle shows us the carrier envelope phase. So here we get the largest current for a carrier envelope phase of pi over 2. This was a sine pulse in the electric field, meaning a cosine pulse in the vector potential. Makes total sense, like expected. And now watch what happens if we go to this, and especially to this case. We also see relatively large currents, but not at pi over 2 anymore, but closer to pi. So now it really seems that the current largely originates from the interfaces, because at the interface we would expect the largest current at a carrier envelope phase of 0 or pi, because this means now the electric field symmetry is maximally broken. So we interpret this data as going from controlling real charge carriers inside of graphene here to virtual charge carriers taken over here. And let me show you something interesting resulting from this. We were wondering, can we use this? I mean, is this interesting? So we thought, why don't we fire laser pulses simultaneously both at graphene and at the gold graphene interface? And now what's interesting, you saw it earlier, the current is now really dependent on the exact field form here, which you call field form A or field form B. And now we could say, okay, let's just say we put bit information in here. Bit 1 means certain waveform, bit 0 means another waveform here. Same here, bit 1 means certain waveform, bit 0 means another waveform. And then the output current is defining the logical output bit. So as you see here, we're now going after a light field driven logic gate. We thought, can we build a logic gate based on this? So we just say the output bit is only set to 1 if there's a current flowing to the right. Excuse me. And then watch what happens. We can now play with the carrier envelope phase of pulses A here, play with the carrier envelope phase of pulses B here. And for A, for example, we only toggle between plus pi over 2 and minus pi over 2. Plus pi over 2 just means current flows to the right. Minus pi over 2 then, of course, means current flows to the left. And here with these pulses, we just play with carrier envelope phases of pi over 2 and 0. If you pay close attention, pi over 2 means here no current. No current, makes sense. 0 means we have a current, but flowing to the left. So now we just have to add up these currents. Only here we have a current flowing to the right, but no current here. So yes, we have a current to the right. Great. Output bit set to 1. Here, these two currents just eat up each other. Output bit set to 0. Here we have a current flowing to the left. Output bit 0. Even more current flowing to the left. Output bit still 0. And now you see here, this is nothing but a logic table. And when you define this here at input bit 0, this here at input bit 0, this here as input bit 1, and this here as input bit 1, then you see 0, 0 gives 1, 0, 1 gives 0, 1, 0 gives 0, 1, 1 gives 0. You see it, this is a logical NOR gate. You only get 1 if neither of the input bits is set to 1. Does it work? Let's try. This is simulation of the currents. This is experiment. You see here we now just vary the carrier envelope phase of pulse A versus carrier envelope phase of pulse B. And you see here experiment and simulation almost fit perfectly. These are just basically measurement artifacts here, these funny stripes. And so this works. And we can even identify more positions, not only 4 positions like I've shown you before, but you can easily identify 16 positions here. And not only build the NOR gate, but you can also build an AND gate or an OR gate or a NAND gate. It's all in here. It just depends on which combination of carrier envelope phases you choose. And you have all the logic builds that you want. So in essence, you can now build a little circuit that might be very fast. This individual logic gate is certainly, if you want, petahertz fast in terms of driving. Does it allow a petahertz logic? Probably not, because in the end, the information is in the current. So we're again RC circuit limited. Here we're working, we're scratching our heads. What can we do? But this initial encoding of a logic bit is really based on the waveform of a laser pulse. Hence, we believe it's a petahertz fast logic bit. And this I'm showing in many talks. I'm not showing it because there's famous names here on this author list. This now takes us one step further, and I love it, I have to say. Our host, together with smart people here, realized that when the electrons are driven fully coherently, why not go one step further? Or why not just come up with a classical logic bit? Why not come up with a quantum logic bit? And this is beautifully laid out here in this recent paper, where now the logic bit information and even a 2-qubit gate is encoded in the population of this band structure. And you see here now 4 bands, and you basically need this combination of Dirac crossings to realize even a 2-qubit gate of this. I can only refer to this here. What's interesting, Kofi, we were just thinking, okay, let's go there. Let's try this. So I was looking hard for materials, and it was fantastic that we have a theory group right next door here around Andreas Görling, and we also have fantastic synthetic chemists that can make all kinds of carbon structures here. This here, beta graphene, has this very interesting chemical bond structure. You see now there's all of a sudden double bonds and stuff. But here we see that we can have band crossings, several, but you can see here they're along different crystallographic orientations. So it'll be exceedingly hard to somehow not only get drive the electrons here, but basically also drive them around the corner. I'm not so sure if this is possible, but it was fascinating to see that this beta graphene, in principle, shows a similar band structure. So We have to find the proper band structure. That brings me to the last part of the talk. In the next 15 minutes, I want to show you something that might help us to realize a suitable band structure, even though we don't have the material as such. We don't have that little piece of whatnot, carbon or so, that allows us to realize this band structure. But we want to now go one step further and generate a new band structure based on periodic driving. And you probably know this famous Kapitsa pendulum. Let me show you this movie. I hope you can see it. I'm not starting it yet. So this is just a little weight. This is the pivot point here. So when this gentleman here lets go, this is just a pendulum that will be down here. But then they can turn on periodic driving, like shown here. So you just drive the pivot point of the pendulum up and down, and then something very interesting will happen. I'm not sure if I hope you can see it. You see it's just falling down. And now, oops, I'm sorry. No idea that. Okay. I hope it's not distracting you too much. You see there is a new ground state. All of a sudden, when the driving is on, the pendulum points up. Let me stop this here. And see, this is really cool. Sorry, I had no idea that that you hear something next to it. What's interesting is by periodic driving, we can generate very counterintuitive states. We can generate this state with a new ground state is the pendulum pointing up, even though, of course, gravity is still there and would point it down. And periodic driving has led to extremely interesting classes of materials. Several of those can be cast under this fantastic new material called the Flow-K topological insulator. So it's Flow-K driving. I'm going to show you in a minute what that is. Flow-K driving that leads to new quantum states, which have been explored with cold atoms in an optical lattice, or have been explored in optical waveguides. But do they exist in real materials? And let me show you in a bit more detail what people have suggested to happen at graphene. You've seen graphene here. We have, again, at the K point, at the K dash point, we have the valence band touch the conduction band. And when we now just shine circularly polarized light, something very interesting happens. A band gap opens up, as you can see here. So this is now just the new light-dressed valence and light-dressed conduction band structure. And what's color-coded here is Barry curvature. Also, Barry curvature shows up. And you see here, it's the same sign of the Barry curvature here and here. So when you integrate over the Brillouin zone, you see here that the Barry curvature in one band actually is not just averaging out to zero. This means that this is a topologically interesting material that we have at our disposal here. This was predicted in this paper, and there's really beautiful initial work by the Hamburg group that observed that basically, well, I don't have time to discuss. We'll get back to this in a minute. But let me show you what's behind this. What's behind this Flow-K physics or this Flow-K Bloch bands? Like before, we now just replace the crystal momentum with the crystal momentum plus the vector potential of the light field, circularly polarized. When you apply that into your time-dependent Schrödinger equation and do a Flow-K expansion, this is what you get. Hold on, right. You get replicas of the initial band structure. So in blue here, this would just be the initial band structure. And now we get positive and negative replicas of this initial band structure shifted by the energy of one photon. And we don't just get one shifted up and down, but we get actually infinitely many. And what's very interesting is that there's also these off-diagonal block elements that lead to a hybridization. So you see here, we get the hybridization of these bands, and this leads to a new Flow-K Bloch band structure under periodic driving. And this is so interesting. Whoops, I'm sorry, I don't know what happens here to the case. This is so interesting because now we can drive electrons in this new band structure. So we just take a light pulse, a circularly polarized light pulse to generate this new flow K band structure, and we take another light pulse to drive electrons in this band structure. And just to show you what we do when the frequency ratio between this driving pulse, the dressing pulse and the driving pulse is 2, we're actually not really probing what happens here where the band gap open at the K point, but we're actually probing here. When we use the second harmonic, we probe something that happens over here. And this is interesting. I'm not aware that other people have done that. We're now really probing, if you will, flow K topological insulators pretty far away from this slightly open band gap. You can calculate the density of states. Of course, interesting stuff happens there. Let me just show you one example. And here's how we do this. So again, we have our graphene, and now we just take 2 laser pulses. As I said, we take 1 laser pulse that drives graphene into this flow K topological insulator state. This is a circularly polarized laser field. And we take a second laser field, which is actually the second harmonic of this one, but linearly polarized. The resulting band structure basically looks like this here. So when you look at the resulting band structure, it looks very confusing. It's also interesting, as you will see in a minute. But what's more important is that we have this driving band structure that really changes our graphene transiently. And we have this control band structure with which we then drive electrons in this new light-dressed state. For this now, we actually go to 50 and 50 nanometer laser pulses. Actually, I just realized I didn't mention any of the parameters before, right? I think a slide somehow disappeared from my talk. Before, we were using 800 nanometer light. Now, titanium sapphire lasers. Now we go to telecom wavelength. As you can see, we now use a femtosecond laser at basically twice the wavelength. That means that the second harmonic now is again around 800 nanometers. So this is the second harmonic. The circularly polarized drive is around 1550 nanometers. And watch what happens. Here's something that I really like. So when we now shoot this dressing field, I mentioned already that we generate a Berry curvature. So what you can see, you know, we're looking at K and K dash, and we're looking at the Berry curvature that's shown here. And now let's just shoot a linearly polarized laser field, right? We know what happens. This is again Bloch's acceleration theorem, now written in a time derivative fashion, right? So it's K dot is just basically given by the E field of the laser. If the E field is polarized vertically, then of course the electrons are also driven vertically. But now this is so beautiful. We have to to find out what the trajectories of the electrons in the material are. We also have to take the Berry curvature into account, because there's no non-finite Berry curvature here and here, and this K cross omega term basically makes the electrons bend around. Right? So we drive them in this direction, but we should generate a current in this direction. This is exactly analogous to the Hall effect, right? If you have a magnetic field pointing in this direction, you have electrons along this direction, you would measure a Hall voltage along this direction. But there is no magnetic field here. It's just the Berry curvature. That's why this is called anomalous Hall current generation. Basically, Hall current generation without a magnetic field, but with Berry curvature. So the Berry curvature takes over the role of the magnetic field, leading to what people call anomalous Hall current generation. Do we see this? Yes, we do. So this is what we shoot at our graphene circularly polarized laser field plus second harmonic linearly polarized. The linearly polarized field is aligned this way, and these are our gold electrodes. And what we see is that we nicely see a current generated here. We can now change the time delay between this dressing and the driving field continuously. This is what you see down here. This is what's plotted on this axis. We now just continuously change the time difference between these two fields. And this allows us to really measure this anomalous Hall current. and you see it just follows sinusoidal motion, it just reflects the fact that we're sensitive to the phase of our FTI state. And this is now here encoded in this waveform. When you add a circularly polarized omega field with a linearly polarized 2 omega field, then you get these Lissajous figures that look like this, or like this, or like this, or like this, depending on the timing of these two fields. And we see here that we get a nice reversal of the current when we just flip or go to the mirror image of the Lissajous figure. We just see we go from minus 200 picoamps to plus 200 picoamps. And if we continue, back here we go again to minus 200 picoamps. That, I think, brings me to the end. It's interesting to realize that we get valley polarized Hall currents here and here. I'll leave it here. Let me come to the end. This is this wonderful team of people that we have here in Erlangen. The ones that are responsible for the data I showed you today were the ones that are highlighted in red here. Dan Lesko, Weijie Li, Selina Nacker still being with me. Christian Heide is now assistant professor in Florida. Toby Weitz is exploring the world right now as a Simon Wittigschlager. This was just our work on graphene. We also work with free electrons from needle tips. We also work with free electrons inside of electron microscopes and little chip-based particle accelerators. But I thought for you, the strong field physics in graphene is the most interesting one. With that, let me come to the end. I hope I could convince you that this beautiful Landau-Sena-Stückelberg-Majorana physics is a reality. What does it mean? It means that we have fully coherent control over electron dynamics. It's really coherent electron dynamics in graphene. Why is it interesting? Because this is just room temperature graphene. No special material, not even cooled down. Why are the electrons coherent? Because we drive them so fast. Everything happens basically within a cycle of the light field. It will be super interesting to see for how much longer this can hold. That's why it's now interesting to go to longer laser pulses where the dynamics takes place over twice as long timescales. What's interesting, we can really also use this Landau-Sena-Stückelberg-Majorana physics for interferometric band structure retrieval. And it will be very, very interesting to really set out and now measure influences of electron coherence. Probably much more interesting influence of electron correlations if we go, for example, to other 2D materials, go away from graphene. Will be interesting if we can really use this for any application around petahertz electronics. And I think what's also very, very interesting is these light-dressed materials, these light-dressed new states that generate from taking a material and light dressing it. We could already demonstrate this all-optical anomalous Hall effect. It will be very interesting to see if we can really come up with new light-dressed designer materials, generate new photonic states, have coherent electron control therein. So I think there's much to come. What's very interesting, if we zoom out a bit, this is attosecond electron dynamics, coherent electron dynamics inside of metallic or semi-metallic matter. Could be very interesting for future applications, I guess. And what's out there, definitely correlated materials, petahertz electronics, maybe even based on Sergei Shevchenko's fantastic proposal, petahertz quantum information, maybe on light-dressed materials. With that, thank you very much for your attention. I look forward to any question you may have.
Thank you very much, Peter, for the wonderful talk and beautiful presentation.